Many people interact with artificial intelligence every day without truly understanding what is happening beneath the surface. Tools like ChatGPT often feel like thinking machines, but they are not minds in the human sense. They are large mathematical systems trained to recognize patterns in enormous amounts of data. At their core, modern AI systems are built from neural networks, layers of interconnected mathematical functions inspired loosely by the human brain. During training, these networks are exposed to vast data sets containing text, images, audio, or video. The system repeatedly makes predictions, measures how wrong those predictions are, and adjusts its internal parameters to reduce error. Over time, this process produces a model that can generate language, recognize images, or make decisions with remarkable fluency. What looks like understanding is actually extremely sophisticated pattern completion, predicting what comes next based on statistical structure learned from data. This is why AI can sound confident even when it is wrong. It does not know facts the way humans do, nor does it reason from lived experience or self-awareness. It operates within a learned probability space. When you ask a question, the system evaluates countless possible responses and selects the most likely continuation based on its training. This makes modern AI powerful, flexible, and scalable, but also fundamentally different from human intelligence. It has no desires, no emotions, no consciousness, and no internal sense of meaning. This distinction becomes especially important when discussing artificial general intelligence, often called AGI. General intelligence refers to a system that can understand, learn, and apply knowledge across a wide range of tasks at a human level or beyond. A true AGI would not be limited to one domain, like language or vision. It could transfer learning from one problem to another, reason abstractly, plan long-term goals, adapt to new environments without retraining, and potentially improve itself. In short, AGI would resemble the flexibility of human cognition rather than the narrow framework of today's AI tools. Whether AI will reach general intelligence remains one of the most debated questions in science and technology. Some researchers believe AGI is a natural extension of current systems as models grow larger, more multimodal, and more autonomous. Others argue that something fundamentally missing, such as true understanding, embodiment, or consciousness, cannot be achieved through scaling alone. There is no scientific consensus, and timelines vary wildly. Some predict decades. Others believe it could happen much sooner. Still others doubt it will happen at all. What is clear is that progress is accelerating. Advances that once took decades now occur in years or even months, driven by better algorithms, more data, specialized hardware, and massive investment. Still, speed should not be confused with inevitability. Complex intelligence is not just about processing power. It involves deep questions about cognition, perception, and meaning that remain unresolved. While AGI is still theoretical, today's AI is already being embedded into the physical world. In robotics, AI enables machines to perceive their environment through cameras, LiDAR, and sensors, interpret that data, and act on it in real time. Industrial robots use AI for precision assembly, quality control, and adaptive movement. Service robots rely on AI to navigate spaces, interact with humans, and learn from feedback. In everyday appliances, AI quietly optimizes energy use, predicts maintenance needs, personalizes settings, and responds to voice commands. Smart thermostats learn your habits. Refrigerators track inventory, Washing machines adjust cycles automatically. In cars, AI plays a central role in advanced driver assistance systems and autonomous driving research. It processes sensor data to detect pedestrians, recognize traffic signs, predict the behavior of other vehicles, and make split-second decisions. In aviation, AI is used for flight optimization, predictive maintenance, air traffic management, and pilot assistance. These systems do not replace human pilots or drivers outright, but they increasingly act as intelligent co-pilots, handling complexity, reducing human error, and improving efficiency. Across medicine, finance, logistics, and manufacturing, AI systems analyze patterns at a scale no human could manage, supporting better decisions and uncovering insights hidden in massive datasets. This rapid integration naturally raises fear and concern. Some worries are valid, others are often misunderstood. People should not fear AI as a conscious entity plotting against humanity. Current AI does not have intentions or self-preservation instincts. It cannot want anything. The real risks come from how humans design, deploy, and govern these systems. Bias in training data can lead to unfair outcomes. Over-reliance on automated systems can erode human judgment. Poorly secured AI can be misused for fraud, surveillance, misinformation, or cyber attacks. Job displacement is a serious concern, especially for roles involving routine cognitive tasks, and societies must adapt through education, reskilling, and policy rather than denial. What humans should be worried about is not intelligence itself, but alignment and responsibility. AI reflects human values, incentives, and blind spots. If deployed without transparency or accountability, it can amplify inequality, concentrate power, and make harmful decisions at scale. If used wisely, it can extend human capability, reduce suffering, and solve problems that have long resisted progress. The question is not whether AI will change the world, it already has, but whether humanity will guide that change with wisdom. AI should be seen as a tool of unprecedented power, not a replacement for human purpose or moral judgment. It excels at processing information, identifying patterns, and optimizing systems. Humans remain essential for setting goals, defining values, exercising empathy, and bearing responsibility for consequences. The future of AI is not a battle between humans and machines. It is a test of human maturity, whether we can build, control, and coexist with a technology that mirrors our intelligence without inheriting our worst flaws. What is often missing from public discussions is the enormous energy demand required to build and operate modern AI systems. Training large-scale models consumes vast amounts of electricity because it involves running millions or billions of mathematical operations repeatedly across specialized hardware such as GPUs and TPUs. These processors are designed for parallel computation, but they draw significant power and generate substantial heat, which must be managed through energy-intensive cooling systems. Even after training is complete, AI continues to consume energy during deployment. Every prompt processed, image generated, recommendation calculated, or voice command interpreted requires real-time computation across data centers distributed around the world. This energy is used primarily for three purposes: computation, data movement, and cooling. Computation involves matrix multiplications and probabilistic calculations at extreme scale. Data movement includes transferring model parameters, user inputs, and outputs across servers and global networks. Cooling is necessary because dense clusters of high-performance chips generate heat that would otherwise damage hardware or degrade performance. In many large data centers, cooling alone can rival computing itself as a major energy expense. As AI systems become more capable and more widely used, inference, the everyday use of trained models, can collectively consume as much or more energy than the original training process. Whether this level of energy consumption is sustainable is a serious and unresolved question. Economically, energy costs directly influence who can afford to build and operate advanced AI. This tends to concentrate power in the hands of a few large corporations and governments that can absorb infrastructure and electricity expenses. Smaller organizations may depend on shared platforms rather than owning their own systems, reinforcing centralization. Environmentally, the impact depends heavily on how electricity is generated. AI powered by fossil fuels contributes to carbon emissions, water consumption for cooling, and strain on electrical grids. In regions with cleaner energy mixes, such as hydro, nuclear, wind, or solar, the environmental footprint can be significantly reduced, but not eliminated. The long-term viability of AI at scale will depend on efficiency gains and energy innovation. Researchers are actively working on more efficient algorithms, smaller models that perform competitively, specialized low-power hardware, and better cooling technologies. There is also growing pressure to align AI expansion with renewable energy infrastructure and carbon accountability. The challenge is not simply technical, it is economic and ethical. Society must decide how much energy it is willing to allocate to intelligence amplification, who benefits from that energy use, and who bears the environmental cost. In this sense, AI is not just a digital phenomenon. It is a physical one, grounded in power plants, transmission lines, water systems, and global supply chains. Understanding AI, therefore, requires understanding energy. The future of artificial intelligence will be shaped not only by algorithms and data, but by how responsibly humanity manages the physical resources that make intelligence at scale possible. If you found this video useful, please subscribe to help keep the channel up for more deep dive explanations like this. Like this video to help it reach others, and comment to help shape what we explore next. Thank you.